Hey, calculus students, welcome back. Let's take a look at the instantaneous rate of change. The instantaneous rate of change is the rate of change in a function at a single instant in time, as opposed to an average rate of change, which is a rate of change over a period of time. The instantaneous rate of change is exactly the same thing as the slope of the tangent. And it was this remarkable conclusion that the world came to by discussing the results of Sir Isaac Newton and Gottfried Leibniz. Let's take a look at this practice problem. I kind of get the day off today. If you'll notice, everything's a practice problem, but not really. But I want you to do everything first, even if you don't know how to do it, or even if you get it wrong, because I want you thinking about the derivative. Isaac traveled to the roof of a tall building and dropped an apple from the height of 30 meters. Ignoring air resistance, the vertical position S of the apple above the ground t seconds after its release can be modeled by S of t equals negative 5t squared plus 30. So just a quick word, S is often used in math class to represent position. We also use X for X position and Y for Y position. S is just kind of a generic variable for position. Find the time when the apple is 10 meters above the ground. Okay, so starting now, please go and work these problems. Go all the way through H. Or do them one at a time. Anyway, regardless, if you're back and you've unpaused it, let's work them. So, like I said, you can do one part at a time and then pause it and redo it, but I'm going to assume that at this point you've worked them all, even if you are pausing as we go. So to find the time when the apple is 10 meters above the ground, I'll simply put a 10 in here, and I'll solve for t. So I get negative 20 is equal to negative 5t squared. And I'll divide both sides by negative 5. So that gives me 4t squared. And I'll take the square root of each side. We'll say the answer is plus or minus 2. But we can't have a negative time, so the answer is simply 2 seconds. Just a quick note, those of you might be wondering where I'm getting the 5 from in this equation when you've seen something similar to it. For simplicity, I'm letting gravity be negative 10 meters per second instead of negative 9.8 because I don't want to deal with decimals. And I hope you'll forgive me for this lack of precision. Okay, part B. What is the average velocity of the apple from the time he let it go at t equals 0 till t equals 2 seconds? Use proper units and show the steps you use to find your answer. Okay, so the average velocity is going to be the change in position. So it's the change in S over the change in time. The change in time is a change from 2 to 0, right? So it's going to be the position at 2 minus the position at 0 divided by 2 minus 0. So the position at 2, we already solved for that one. That was 10. That's how we got it to begin with. And then S of 0 was 30. All over 2 minus 0 is 2. So that is a negative 20 over 2. So a negative 10. And what's the units? Well, the units, when you find a rate of change, velocity is the rate of change in position, is always the y units divided by the x units. So for me, the y units on this problem is the vertical position, which is in meters, right? So vertical position, so it's going to be meters per x value, which is, or t, which is seconds. It's always the y variable over the x variable, always. Because that's what we're dividing. We're dividing change in position. This is meters, and we're dividing by change in time, meters over time. So meters per second. What is the average velocity of the apple over time 1 to 2? Well, we just need to do a similar procedure. So I'll find the position at 1. I'll subtract the position at 2 over 1 minus 2. And I could have done S of 2 minus F of 1 over 2 minus 1. It's the same thing, as long as I have these things line up. So what's the position at 1? Well, our equation was negative 5t plus 30, so it would be 25. The position at 2 was 10, right? And that's a negative 1. So this is a negative 15. Positive, yeah, positive 15 over negative 1, which is a negative 15. That's the answer. But we need the units. Always need the units on these problems, please. Very important. They grade them. They're worth as much point as the answer. Meters per second. So it seems like the average rate of change is bigger from 1 to 2 than it is from 0 to 2. Create a formula for calculating the average velocity of the apple from any time t to t equals 2 seconds. All right, well, we can do that, right? So we're going to go any time t. So the average velocity at any time t to 2. Average velocity, I'm going to say, from time t to 2, or 2 to t. It would all work out the same. So the average velocity is, the position at t is s of t, right? Now the position at 2, when you plugged in 2 to the equation, we got 10 over t minus 2. We're going to use a calculator and our formula from part D to complete the following table for the average velocity. So let's do it. Okay, I'll use Desmos here to do this. And I'm going to make a function for s of t, which was negative 5t squared plus 30. I'm doing some kind of fancy, function stuff on it in Desmos. You can just use it as a regular scientific calculator. You don't need to be, you can be as fancy or not fancy as you want to be. That's perfectly fine. And so I am going to say that this is going to be s of 1.9 minus s of 2 all over 1.9 minus 2. So that's going to make this a negative 19.5. Now, then I can change this to a 1.99, etc., and go from there. I can even make this like an x, and then I can get a table of values for it for different values of x. So that's kind of cool, right? Can't do 2 because it wouldn't be defined there, right? All right, so those are the values that you should have in your table. I'm just going to transfer those over so we have them and are documented here. Okay, so what is that 19, negative 19, that should be a 9.5, not a 2.5. I'm not sure why I wrote that. Negative 19.95. Well, that whole thing is just completely unreadable, isn't it? All right, so we can look at this and kind of get an idea for what's happening as we get closer and closer to getting the exact instantaneous velocity. Okay, the vertical position s of an apple dropping 30 meters, that's just to remind you, because I think we turned a page there. As opposed to average velocity, which exists over an interval, the instantaneous velocity exists in a single moment of time, and that's the real question. Can we define a rate of change at an instance of time? And that's what calculus is all about: trying to determine a rate of change at one specific moment and not over an interval. So in our table, we were looking at rates of change over intervals. But could we use this to make a prediction about what we think the instantaneous velocity is? Certainly as we get smaller and smaller units, of change, it looks like we're getting closer and closer to negative 20. So let's try 2.00001. 2.00001. It's getting really close. And it appears to be doing that from no matter which direction. If I come to 2 from below, it's also approaching negative 20. So I think it's safe to say that this limit is approaching the same value. So I'm going to say that my guess is that this is negative 20 meters per second. Let's use the limit process to verify our answer to part F. So let's take a limit. We're going to take a limit, and I can use any variable I want here. I'm going to say t. I'm going to take a limit as t goes to 2 of s of t minus s of 2 all over t minus 2. Now, s of t was a negative 5t squared plus 30, and s of 2 was 10. And so they have the limit as t goes to 2 of a negative 5t squared plus 20. Let me just bring that over here. Limit as t goes to 2 of a negative 5. I can pull that out, and I get t squared minus 4 over t minus 2. That's a 4, not a 9. Okay? And so then I have the limit as t approaches 2 of negative 5 times t minus 2 t plus 2 all over t minus 2. That reduces out, and I have the limit as t approaches 2 of a negative 5 times t plus 2. I'll plug in. I have negative 5 times 2 plus 2 is 4, and I get a negative 20 meters per second. So our guess was correct. That is the correct value for this instantaneous velocity. That is the slope of the tangent line there. All right, let's bring this conversation home by just summarizing this, making that connection to the slope of the tangent line. So I want to leave what we just found there in case we need to come back and reference it. And let me just copy this over. So the instantaneous velocity is the instantaneous rate of change of position. The instantaneous rate of change of a function, f of x at x equals c, is equal to the slope of the tangent line at x equals c. The instantaneous rate of change of f is denoted f prime of x. The function s of t equals negative 5t squared plus 30 is graphed below. I want you to sketch a line to s at t equals 2. What is the slope of this line? So let's sketch that line first and foremost. So at t equals 2, just like we said, we're at 10. And that's kind of my estimate of what the tangent line would be. Well, what is the slope of that tangent line? The slope of that tangent line has got to be negative 20. Why? Because that was the instantaneous velocity. And we call it instantaneous velocity because s is position. But if s was temperature, it would be the instantaneous change in temperature. Sometimes we have a nice word for it, like velocity. Sometimes we don't. Whatever it is, that slope of the tangent line is the instantaneous rate of change of the y variable over the x variable. All right, what I'd like you to do now is try and practicing applying what we just kind of discussed. So please work practice 5.2. Pause the video, work it, and then we will go over it. All right, practice 5.2. The table below shows selected values of a continuous function, w of t, representing the amount of water in a holding tank in cubic feet at time t hours. Use the calculators needed to answer each. What is the average rate of change in the volume of water over time from 0 to 5? Use proper units and show the work that leads to your answer. Average rate of change is simply going to have the units of the y variable over the x variable. And like I mentioned earlier briefly, when working a problem like this on the AP calculus exam, and there will be a problem like this, they're going to give you as much points for the units as they do for the actual numeric answer. You must get the units. Okay, so let's go ahead and find this change in volume from 0 to 5. So an average rate of change is equal to the change in the y-coordinates. So that's 23 point. Actually, you know what? I'm going to show just a little bit extra work. You don't have to show this, but since this is w of t, well, I used x and y earlier, but that was to make a point. But this is, we're graphing t as our x, and this is w of t as our y. So it's w of 5 minus w of 0, because I'm going from 0 to 5, over 5 minus 0. I want that pattern in your head. F of the x2 minus f of x1 over x2 minus x1. Now, w of 5 is 23.9 minus w0 is 6.5. And then the bottom is 5.5 minus 0. And the units are the y variable, in this case the w variable, foot cubed of water per hour. Okay, and that represents the amount of change in the cubic feet per hour. Now you might be wondering, why didn't I get an answer? Well, I think it's worthwhile for us to go ahead and get an answer, so we'll do that, but I am hesitant to write it down, because if this is a multiple choice question, yes, you're going to have to give a decimal answer, but it's most likely a free response. And on the AP free response, you don't have to evaluate anything. You just have to set it up. I wrote it that first step here because I want to make sure that you know that you can't leave it like this. You cannot do that. That's not allowed. You can do that and I want you to do that as an initial step, but you have to go to where you substitute in the values from the table and then stop there. Now, if you have a calculator, I still want you to stop there. I didn't even subtract 5 minus 0. You get no bonus points for doing it. And in fact, if you go over the grading rubrics, you'll actually see they make comments where they'll say something like, the student at this point has earned the full 2 points for this problem. They continue to simplify further, even though they don't have to, and get the right value, so it's correct. Other times you'll see them say the student has earned the full 2 points, they continue to simplify further, but must have made a mistake in their calculator, and now they lose 1 of the points. So you can only lose credit, you can't gain it. So if it's not a multiple choice question, just leave your answer like that. But since we're learning and exploring, it might be satisfying to know what this value actually is. So let's go ahead and do it. But I'm not gonna jeopardize my beautiful work by actually putting it in. 23.9 minus okay, starting over here. 23.9 minus 6.5 over 5 minus 0. So 3.48 cubic feet per hour. Now, yes, in the real world, we're going to want that number. But if it's a test that affects college credit for you, I don't want you getting credit depending on whether or not you accidentally hit an 8 or a 9 when typing in 23.9, especially if you're nervous. So just don't risk it. All right. Letter B. Estimate the value of W prime of 2.5. Use proper units and show the work that leads to your answer and explain the meaning of the value in terms of the situation. So the meaning of this value, which we got was 3.48. That's the average change in the volume over the 5-hour period. The meaning of W prime of 2.5 is the change in volume at that moment. It is the rate of change of volume at that moment in time. All right, so let's go ahead and calculate that. Well, we can only really estimate it, and it's a good idea, although they don't count all for it, but it's a good idea anytime you're using a table to estimate a derivative to use these is approximately. Now, if they give you 2.5, which value should I use for my hours to get the estimate? Well, if 2.5 was in the table, I definitely want to use that as one of my values. But if it's in between two values from the table, I just have to use the two that are closest to around it. Don't use 0 and 5. Those are not as close as you can get. So I'll do w of 3 minus w of 2 over 3 minus 2. Now I can't leave it like that though. I have to go ahead and go further and actually plug in 20.5 minus 17 over 3 minus 2. And that is also in cubic feet per hour. The rate of change, the average rate of change and the derivative have to have the same units. They have to, because they are both rates of change of the function. So can we conclude if there was a time when the volume of the water, let's go ahead and go back. I'm sorry. It did say explain the meaning, so let's write it. Let's just say this is the rate of change of volume at t equals 2.5 minutes. And that's how you always want to say it. If they ask you what does the derivative at this value mean, you simply want to say that is the rate of change of whatever this function is a function for at whatever time it is they gave you. Can we conclude if there was a time when the volume of the water was exactly 20 cubic feet? Well, I think we certainly can. In between time hour 2 and hour 3. Let's make sure that we set it up properly. It did mention that it's a continuous function right there. So we'll say that. We'll say that W is continuous. We're going to say that W of 2 is less than 20, which is less than W of 3. So therefore, by the intermediate value theorem, which we can abbreviate IVT, W of t equals 20 for some value t on the open interval from 2 to 3, or t greater than 2, less than 3, however you want to write that. Okay? All right, you have one more practice problem to do. So if you would go ahead and give it a try, practice 5.3. Okay, so hopefully you've paused the video and given it a shot. Let's go over it. The graph below demonstrates the velocity of a particle moving horizontally along the x-axis over a time from 0 to 6. Use the graph to estimate the acceleration of the particle at times t equals 4. So this is the velocity of the particle that's moving along the x-axis. So this here is velocity, and this here is time. Acceleration is simply a rate of change in velocity over time. So to estimate the acceleration of the particle at time t equals 4 means that I need to estimate its tangent line. And this one's not that easy to do. It's something like this maybe, or maybe it's, can't really tell which side of the curve it would be on or if it goes through it. Okay, so I'm going to estimate that as a negative 2 over a half. So the slope of this tangent line appears to be the change. The change in this tangent line slope appears to be a negative 2, and the change in the run is a 0.5. So I'm going to call this negative 2 divided by 0.5. So that's negative 4. And that would be, well, we didn't describe the units, so we don't have to give the units if they don't give them to them. But if this was, let's just say this was in meters per second, then this would be in meters per second. That's the units on velocity over second. So it's meters over second, or meters per second squared if you combine them. What is the acceleration? 0. Well, the acceleration is going to be 0 whenever the rate of change is 0, which means that the tangent line is got a slope of 0, and that's going to occur here and here at approximately, and I'm not being exact here, but approximately t equals 2, and looks like t equals 5. Is the particle moving left or right at t equals 2? So at t equals 2, is it moving left or right? Well, is the velocity positive? So because velocity is greater than 0, we must be moving to the right, towards positive. And that's just kind of conventional Usually they'll tell you the moving along the x-axis, this puts their position. So if the position is getting more positive, velocity is saying our velocity, our rate of change is 2. It's moving 2 per second further along the x-axis. It's definitely moving right because the velocity is positive. Down here where this curve is negative, we would say it's moving to the left. And we're going to talk a whole lot about that and practice that a whole lot in the future, but I think it fits in right there really well. So that's the end of today's lesson, and I hope you enjoyed hanging out in Newton's house for a little while and how he developed and used calculus. Until next time, take care.